Designers must understand how a linear circuit reacts across an entire spectrum of physical frequencies to prevent system failure. Analyzing a single signal is insufficient for predicting how a complex circuit will behave in the real world. We transition from the theoretical Laplace S-domain transfer function to the physical frequency domain by substituting S with j omega. This reveals the two distinct components of the system, magnitude response and phase response. To handle wide frequency ranges, we use a mathematical shortcut, representing the gain in decibels. By applying 20 log base 10 to the amplitude, the difficult polynomial multiplication of a transfer function becomes simple graphical addition and subtraction. Before plotting, the function must be standardized. Every pole and zero must be forced into the format of 1 plus s divided by omega 0. This standard form is a foundational requirement for accurate analysis. Failing to extract these constants results in an incorrect baseline DC gain, which shifts the entire plot vertically and masks the true behavior of the system. This image illustrates the foundational shapes of a Bode magnitude plot: constant k, an origin 0, and trajectories for a simple 0 and pole. We measure these slopes across a decade. Zeros rise 20 decibels per decade, while poles fall 20 decibels. Consider this single-time constant circuit, where the transfer function is 10s over s plus 1000. By factoring out the 1000, we achieve the standard form shown here above the empty logarithmic graph. The isolated constant k equals 1 over 100. Converting this to decibels establishes a baseline gain of negative 40 decibels, which serves as the starting point for our plot. The 0 at the origin introduces a positive 20 decibel per decade slope that begins at the established negative 40 decibel baseline. At the break frequency of 1000, the real pole in the denominator introduces a negative 20 decibel per decade slope. The true magnitude response is the graphical addition of these simultaneous slopes. When the rising 20 decibel slope hits the negative 20 decibel pole, the line flattens, revealing the circuit's stable operating bandwidth. Magnitude alone cannot predict stability. Phase shifts dictate whether feedback in an amplifier will stabilize the system or cause it to oscillate out of control. We approximate the phase of a real pole using piecewise linear rules. The phase shift begins its effect exactly 1 decade before the break frequency. In this case, the line begins to drop at 100 radians per second. The phase drops linearly, crossing negative 45 degrees at the exact break frequency of 1000. It completes its shift at 10,000, 1 decade after the break, settling at negative 90 degrees. This asymptotic model is a deliberate approximation. There is an error of exactly 5.7 degrees at the 1/10 and 10 times break boundaries when compared to the actual phase curve. This logic scales to multipole systems. No matter how complex the transfer function becomes, every new break frequency simply adds to or subtracts from the running slope total. Bode plots translate complex polynomial roots into a visual dashboard. This clarity allows designers to see the physical limits and stability requirements of any linear electronic design.